Hello my dear students, a very good morning to all of you. In the previous class we discussed about the identity relation as well as the reflexive relation. Now the turn of symmetric relation. So today we shall be discussing in this very particular video about symmetric relation, anti-symmetric relation as well as asymmetric relation. One by one we shall be discussing about all those relations with various examples. So we just start the symmetric relation first. Symmetricity means the image of the given element whatsoever exists in that particular relation. Suppose the relation contains A, B, then it must contain, it is mandatory to be BA in that particular set, in that relation. Otherwise it won't be called as the symmetric relation. This is the only definition of symmetricity. So you just take care. Suppose 1, 2 is lying in the given relation and 2, 1 is not lying over there, then in that case we shall be saying that symmetricity is contradicted in this particular case, and then that given relation is not symmetric. So I have just written the definition. You just try to understand, and some examples will also be decided on the basis of that, so that it could be very much clear to all of you about symmetric relation. Just watch. I have just written the definition. A relation over the set A, that is R is a subset of A cross A, is called a symmetric relation if and only if xy belongs to R implies yx belongs to R. That is, if x is R related to y, then it is necessary for y to be related to x with the same relation. If xy is there and yx is not there, then that relation won't be symmetric relation. Suppose in that case that if xy is not lying over there, then we are not bothered about watching whether yx is lying in that particular relation or not. It is only the case that xy should be there. If xy is there, then we shall be looking about yx. If xy is not there, no need of watching whether yx is there or not. We will be understanding all of them with these examples, whatever I have just written over there. Just go on watching the example. We have just supposed that A contains 3 elements, 1, 2 and 3, and R is a relation over the set A. Some examples have been given. Suppose the first example is the relation is R5, that means the empty relation. The second one I have written the universal relation A cross A itself. All 9 elements have been taken into consideration. Again the third relation I have written containing 1, 1, 1, 2 and 2, 1, and the fourth one I have taken 1, 1, 2, 2, 1, 2, 2, 1 and 2, 3, and the fifth one I have taken as 1, 1, 2, 2 and 3, 3. Now one by one we just discuss about those. We shall be discussing about what is that empty relation later on. Here just watch for the universal relation. Whatever the element xy you have got, whether yx is there or not. For 1, 1 you have got yx is equal to again 1, 1. For 2, 2 the same interpretation. For 3, 3 the same interpretation. For 1, 2. If x is 1 and y is 2, then what would be yx? 2, 1. 2, 1 is lying over there. 2, 3 is there. 3, 2 is also there. This is also okay. 1, 3 is there. The symmetry of that 3, 1 is also lying over there. So on the basis of that we conclude that A cross A, that is the universal relation, is a symmetric relation. Now what about the third example? I have taken 1, 1, 1, 2 and 2, 1. Yes, just go on. 1, 1, it's okay. 1, 2 is there. What is the symmetry of that? 2, 1. Again 2, 1 is there. What is the symmetry of 2, 1? 1, 2. So this relation is also a symmetric relation. So whatever we are getting, that universal relation is a symmetric relation. This relation is a symmetric relation. Now watch carefully about the next relation. I have taken 1, 1, 2, 2. It's okay. 1, 2 is there, and the symmetry of that 2, 1 is also there. It's okay. What about 2, 3? 2, 3 is there, but 3, 2 is absent from that particular relation. So we say that the symmetry of 2, 3 is not existing in this particular relation. So we conclude that this is not a symmetric relation. What about the last example, whatever I have just written? R contains 1, 1, 2, 2, 3, 3, which is undoubtedly the identity relation, or you can be saying that a reflexive relation. So whatever the xy is there, just see x is 1, y is 1, then yx should be what? 1, 1. I mean to say the same interpretation is there for all these. So if 1, 1, 2, 2, 3, 3 lies, we don't have to check anything else. We will be saying directly what is that, directly that it is asymmetric relation. So this one is also asymmetric relation. I have just made what is that image of xy like this to make you understand that what will be the image of xy. In the mirror image, I mean to say, would be yx. So this is mandatory to be there. Now we come over this particular relation, that is the empty relation, and just think, this is little bit surprising. You will be surprised to know that R5, that is the empty relation, is also symmetric. On what basis did you say that the fourth one is not symmetric? You said that's why 2, 3 is there, but 3, 2, that means the symmetry of 2, 3 is not lying. Means what? The symmetricity is contradicted in this case, and on the basis of that, you just conclude that this one is not a symmetric relation. In empty relation, we don't have any element, and if you don't have any element, can you argue that the symmetry of that one is existing or not existing? So the benefit of doubt over there means what? You don't have any contradiction in that case. So since the symmetricity is not contradicted in case of the empty relation, so we say that the empty relation is also a symmetric relation. So note it down. This is very, very important. In competitive exams also, it is asked whether the empty relation is symmetric or not. Suppose this question is asked in your board exams in 1 mark or 2 marks, and you have to write something. You need not write much more. You just go on writing in 1 or 2 lines that since the empty relation contains no element, and therefore symmetricity is not contradicted in this case, and hence we conclude that this one is a symmetric relation. Now I just give you some more examples to make it clear. Now just see. I have taken the second example as we have just considered the set of reals R, and we are going to define some relations over the set R. The small r has been taken as the relation for various examples. So A is R related to B if and only if A is equal to B. The next one is A is less than B, the third one is greater than B, the fourth one is less than or equal to B, and the fifth one is greater than or equal to B. Now think like this. If A is equal to B, whether B is equal to A or not, if A is equal to B. So undoubtedly if A is equal to B, then B is also equal to A. So this relation is symmetric, because if A is equal to B, you may say that B is also equal to A. So this one is a symmetric relation. What about A less than B? Anyone can say that if A is less than B, then naturally B would be greater than A. B can't be less than A. So this one is, that is, B is not less than A. So this one is not symmetric. So the first one is symmetric, second one is not symmetric. What about the third one? The same logic as we just gave for the second one. If A is greater than B, then B is less than A. That is, B is not greater than A. So this one is also not symmetric. What about less than or equal to? Here B would be greater than or equal to A. B won't be less than or equal to A. Here B is greater than, less than or equal to A. So B is not greater than or equal to. It means the same relation is not being held by B and A, whatever is the relation between A and B. Had it been B is less than or equal to A, or in this case B is greater than or equal to A, then it would have been, what is that symmetric relation. But here that is not so. So these two are also not symmetric relation. So out of these 5 relations, whatever we have just did previously for reflexive relation also, this was the third and the fourth. That means the relation of equality, the relation of less than or equal to, the relation of greater than or equal to, they were reflexive. Whereas these two were, that means less than and greater than, were not reflexive. Here we find that except the first one, that means the relation of equality, all these 4 relations in the set of reals are not symmetric. I think you have understood this one, a very simple example. Now the third example I am going to recite you about the lines in the xy plane. We have just considered that L being the set of lines in xy plane. It's defined as L1 is R related to L2 such that L1 is parallel to L2. right? Here the relation lies between two lines is what? The relation of parallelism. And the second case, S, we have considered that L is perpendicular to M. That means the relation of perpendicularity is lying over here. So from these two, now you just decide. If L1 is parallel to L2, whether L2 is parallel to L1 or not. By plane geometry or simple geometry, we know that if one line is parallel to another line, then that particular another line must be parallel to the very first line. So this one becomes a symmetric relation. So you can very well say that the relation of parallelism is a symmetric relation. What about the relation of perpendicularity? Whereas it is not reflexive, because no lines can be perpendicular to each other. But here we shall find that this relation is symmetric, because if L is perpendicular to M, M must be perpendicular to L. So if I say that these two lines are parallel, this one is parallel to this one, naturally the second one is also parallel to that. If L1 is perpendicular to L2, naturally L2 is also perpendicular to L1. So both of them, either the relation of parallelism or the relation of perpendicularity, both of them are symmetric relation. So I think you have already understood the symmetricity of the relation. Now after that we shall be dealing with antisymmetric as well as asymmetric, which are none other than the against of this very symmetric relation. But you have to understand those two relations carefully, because they are asked in competitive exams. In board exams you won't get any question from antisymmetric as well as asymmetric, but you will be getting all those things over here for your competitive exams preparation. Anyways, I just deal what is that, antisymmetric as well as the asymmetric relation again. Now guys, let us start for about antisymmetric as well as asymmetric relation. So the given relation R over the set A is called an antisymmetric relation. The condition for that is if xy is in R as well as yx is also there in R, then it is mandatory for x to be equal to y. If both of them lie in R, that means in the given relation, then we have to check whether both of the components of the given elements are equal or not. If any one of them is lying, the other one is not lying, we are not bothered about watching whether the first component is equal to second component or not. In that case, we say that antisymmetricity is not contradicted, and hence we will conclude that the given relation is antisymmetric. Once both of the symmetry are existing in the given relation and the components are not equal, then we shall conclude only that this is not antisymmetric, otherwise it would be antisymmetric. So far as asymmetric relation is concerned, xy belongs to R, yx must not be equal to R. It is more restrictive. It is little bit liberal one. The antisymmetric one is little bit liberal, but it is more restrictive. Why do we say that it is more restrictive? Because here we are not allowed to take even those elements having equal components. That means for antisymmetric relation, we can consider 1, 1 or 2, 2 or 3, 3 or any two of them or in all three of them if A contains 1, 2, 3. Whatever the example I have given over there, right? But in this case, in asymmetric relation, if 1, 1 is there, then that won't constitute a asymmetric relation, because if it says that if xy is there, yx must not be over there. So what would be the symmetry of xy? The symmetry of xy, if x is equal to 1, y is equal to 1, is same 1, 1, and since 1, 1 is lying in that case, we say that that is not asymmetric, whereas it would be antisymmetric if 1, 1 is there or 2, 2 is there or all of them are there. Just watch the examples one by one. The first one I have given, the empty relation, R5, empty relation. How would you, what is that, say, what would you say about the empty relation? How would you justify about this one, the empty relation, whether it is antisymmetric or asymmetric or not? So the same explanation I am going to give, whatever I just gave you for symmetric relation, that if no element is lying in the given relation, we don't have any, what is that, option to check whether the symmetry of the given object is lying over there or not. The same case, in the same fashion, we are going to explain over here also. Antisymmetricity is possible if both xy and yx are lying, and then we shall be bothering about checking whether x is equal to y or not. Here in the empty relation, since no element is lying, that's why we don't have any option to check it out. So again, the benefit of doubt, that means we can say very well that antisymmetricity is not contradicted in this case. Unless or until there is some element for contradiction, we can't say that it is not antisymmetric. So empty relation is undoubtedly an antisymmetric relation, as well as asymmetric relation, because it contains no element. Had there been any xy, then we would have watched whether yx is lying over there or not. Since phi contains no element, that's why on the basis of that we say that the given empty relation is antisymmetric as well as asymmetric, and obviously it was a symmetric relation too. Now what about the universal relation? You just go on watching. Universal relation contains all those elements lying in A cross A. Naturally 1 1 would be there, 2 2, 3 3, 1 2, 2 1. Now you just see, if 1 2 is there, 2 1 is also there. So on the basis of that, or 1 1 is also there, we say that the universal relation is not asymmetric. What about antisymmetricity? 1 2 is there and 2 1 is there, 2 3 is there, 3 2 is there. Are 2 equal to 3 or 1 is equal to 2? No, they are not equal. So we say that universal relation is not antisymmetric. So universal relation is only what? Symmetric, so far as these three relations are concerned, whatever we are discussing today. So the universal relation is symmetric, but neither antisymmetric nor asymmetric. Now the next example I have given, R is equal to containing three elements, 1, 1, 2, 2 and 3, 3. This is, just go on watching, xy is there, again yx is there, because symmetry of 1 1 is what? 1 1 itself, and 1 is equal to 1. The same conclusion or the same explanation for 2 2 and the same logic for 3 3. So in this case we say that the set containing 1, 1, 2, 2, 3, 3 is undoubtedly antisymmetric, but it is not asymmetric. So far as this one, so this one is both. I am just putting two arrows, one arrow for antisymmetry, the lower arrow for symmetry, asymmetricity. A cross A is neither that nor that. So this one is neither antisymmetric nor asymmetric. R, this is antisymmetric but not asymmetric, because the symmetry of xy is there. 1 1, the symmetry of 1 1 is again 1 1. So I have just warned you that the elements containing equal components will not lie in asymmetric relation. So this is not asymmetric relation. What about the fourth one? Again 1, 1 is there. So on the basis of that you can immediately say that this is not asymmetric, but it is a, what is that? It is an antisymmetric relation or not. You just go on watching. 1, 1 is there, 2, 3 and 3, 2 is also lying there. Means what? xy is there as well as yx is there. Is x is equal to y? No, x is not equal to y over there. 2 is not equal to 3. So on that basis we say that this is none of these two. That means neither antisymmetric nor asymmetric. Likewise, fifth one, just go on watching. 1, 2 is there, 2, 3 is there. Here you just watch, very carefully. 1, 2 is there. Does 2, 1 lie over there? No, that doesn't lie. 2, 3 is there, and the symmetry of 2, 3 is also not lying over there. So unless or until the symmetry of 1, 2 as well as symmetry of 2, 3 are lying over there, how can we say whether x is equal to y or not? We shall not be discussing about that. We shall not be bothering about that. So on the basis of that we say that this is anti-symmetric, because we don't have any option to relate it with the symmetry of the given relation, because the symmetry of the given elements are not provided in this one. Whatever I had already warned you earlier, that unless or until the symmetry of the given elements are lying and both of them are equal, we can't say that is antisymmetric. So in this case, antisymmetricity is not contradicted and hence it is antisymmetric. So far as asymmetricity is concerned, again asymmetricity is again not contradicted, because 1 2 is there, 2 comma 1 is not there, whatever the definition says. 2 comma 3 is there, but 3 comma 2 is not there, so this is also asymmetric. Now the sixth one, 1 comma 2 is there, 2 comma 3 is there, 3 comma 1 is there. Just go on watching carefully. 1 comma 2, no. 2 comma 1, 2 comma 3 is there, no. 3 comma 2, 3 comma 1 is there, not 1 comma 3 is there. Means what? None of these three elements have their symmetry. So what is that? This is asymmetric relation. And since no elements of the given relation in sixth one have their symmetry, so we have no right to check whether x is equal to y or not. So in both of the cases, this is antisymmetric as well as asymmetric. Now the last one, just go on watching carefully. 1 comma 1, 1 comma 2, 1 comma 3. 1 comma 1. Since 1 comma 1 is there, that means xy is lying as well as y-axis is also lying. So this can't be asymmetric relation. So this would be what? 1 comma 2 is there, 2 comma 1 is not there, 1 comma 3 is there, 3 comma 1 is not there. That means what? The symmetries of these two elements, 1 comma 2 as well as 1 comma 3 is not lying in this particular relation. So this for antisymmetricity, this is okay, this is also okay, this is also okay. So this is antisymmetric relation, but not asymmetric relation. So be careful while discussing about antisymmetricity as well as asymmetricity. I just again repeat in short, that both of them are against the symmetricity. Antisymmetricity is little bit liberal, whereas it is more restrictive. What do you mean by liberal? Here in this case, in the case of antisymmetricity, we are allowed to take any one of the pair element having equal components, either one of them or two of them or all of them, no matter. But for asymmetricity, we are not allowed to consider the elements, that means the pair elements containing equal components. This is not. That is why I say that this is more restrictive. Anyways, so this is all about antisymmetric relation as well as asymmetric relation. So far we discussed about symmetric relation, antisymmetric relation and asymmetric relation with examples. So I think you all have got over there. Now one thing you just in the end you just try to understand, we just watch that this one is antisymmetric as well as asymmetric. This one is asymmetric as well as antisymmetric. This is the last one is antisymmetric but not asymmetric. So on the basis of that, you can say that asymmetric relation is always a subset of antisymmetric relation. Means the relation whatever are asymmetric is always antisymmetric. Means I just write asymmetric implies antisymmetric. But the converse need not be true. Means the asymmetric relation is always a subset of antisymmetric relation. So this is all for the day. In the very next class, we shall be discussing about the next type of binary relation, which is none other than transitive relation as well as equivalence relation. Okay guys, thank you for watching the video, and I'm just wait for the next video. We shall be meeting over there. Until then, just take care of yourself, stay safe. Thank you very much.